I want to quickly go through this schedule a little bit so you know what's going on. So today we're at week 7. I was supposed to move on to chapter 5 today, but I think we need more time to finish up chapter 19. So we will get into chapter 5 next week. And for chapter 5, we'll be going back to SQL programming again. So you guys will be bringing your laptop again for next week. Okay. And also next week, on Thursday, you'll be doing your presentation of project phase 2. How's everyone doing for the phase 2? Just get started. Okay, I'm looking forward to it. So that will be held in an evening, and I'll ask you guys for the time availability a bit later in the class when we have more people here. Okay, so in total we might take 2 hours, and I will ask you guys what time most people will be available. And we'll be having pizza while watching people's presentation. Okay, and next week we'll get to choose the flavor. I think that will be fun. And I will post homework 3 today, and which will be due in 2 weeks. We also have 2 options for homework 3, because homework 3 actually will include chapter 19 and chapter 5. And for each part, I think the workload will be quite a lot. So I will ask you guys later, so remind me before the class finishes. I'll ask you guys whether you want to split that homework into 2 parts. And you submit the one for chapter 19 first, and then a week later, you submit the one for chapter 5. So you don't accumulate everything until the last one. So that's for that. Okay, so let's get into the lecture for today. If I didn't remember it wrong, last time, I think we finished it around here. Okay. So right here was where we finished last time. We were talking about dependency preserving decomposition. So before I talked about this, let's just quickly review what are the 2 types of decomposition properties that we care about, other than dependency preserving. Anyone remember the other one? When you don't want to lose any information during decomposition, you want to recover it back, and it's still correct. That one is the lossless join decomposition, if you can recall. So for a lossless join, the way we do it is after we decompose original relations, for the decomposed smaller relations, we take a natural join of them, and then we check whether that completely match original. Okay. So here's the dependency preserving decomposition. Last time when we were talking about lossless join, we mentioned sometimes an approach for decomposition might lead you to a lossless join result. However, you might lose some dependency that was given at the beginning. Right? You might lose those integrity constraints, you can say. So let's talk about dependency preserving decomposition today. Let's talk about what's the definition and how we can find whether a decomposition is dependency preserving. So here I list again, I think I talked about here last time, but I'll just quickly review again. So here we all know when we use big R, we are talking about a relation. And let's say today we decompose our relation R into sets attribute of X and Y. Okay? So there are 2 relations, one have attributes X and one attributes Y. So just remember, when we talk about X and Y, we are not just saying single attribute, it will be a set of attributes. And for F, we are saying the given functional dependency is given that hold true over all of the instances in R. So in order to check whether a decomposition is dependency preserving, we want to introduce a really quick concept first. So it's called the projection of F on X. If you can remember, we will denote that as F subscript X. Okay? So the idea is just really like the projection we do for relational algebra. Here are the attributes we want to project on the set of functional dependencies X. Okay? Where all of the functional dependencies in there, if they are saying U determining V, then U and V's attributes should both be in the X attributes. Okay, so here is still a bit confusing, but I'll go through an example later so you can see what I mean by that. So, the definition of the decomposition based on the projection concept we just learned is that the decomposition of relation schema R with function dependencies F into schemas with attribute sets X and Y is dependency preserving if, when we take projection of F on X and in union projection of F on Y, taking their closure, we'll go back to the original closure. Okay, so I just kind of talked through what this means, but here I have another interpretation for that. So if we take the dependencies in projection of F on X and projection of F on Y and compute the closure of their union together, we get back all independencies in the F closure. So let's take a look at the next slide. Everyone got that? So let's take a look at the next slide and we can see what I mean by that. So here we have an example like this. And we want to see whether it is dependency preserving. So what I say here means we have an original R, okay, right here, and we decompose them into two sets of attributes. One is AB, one is BC. And the given functional dependencies for R are these three. And today we want to check if given these dependencies and we decompose it this way, this decomposition is dependency preserving. So as you saw before, in the previous slide, we want to check the projection first. Okay, so let me just write down these questions right here again, and we can work through it. So decompose and for ABC, the function of dependencies right here, we use a set to denote that, right? Because the order of functional dependencies does not matter. So say we have A determines B. We also have B determines C. And we also have C determines A. So since we break down the original R into A, B, and BC, let's first check both of their projection first. So we want to check this one. We want to separately check the projection of F on AB and also the projection of F on B. Okay. So according to here, what do you think the projection of F on BC will include? If you recall, that means if it's projection, it means for this function dependencies, both sides should be from here. Okay? So if we only look at here, judging by these three, which one is the only one that will satisfy? The first one, right? Because the first one, A is in here, and B is also in here. Okay, so we can write down the first one. Then let's take a look at this one. Which one do you think satisfies the projection of F on B? The second one, right? Okay? So far we have these. And you might think, okay, let's just take a reunion and then check whether the closure is the same. However, even though it looks like if we take a union, we only have AB and BC, and if we take the closure, we can infer one more, which is AC, right? And is that completely the same as that one? No. But actually, if you derive here a bit more, we have more function dependencies from here, right? If we derive it into a closure, what else can you see based on A determines B determines C, and C determines A? If we try to use transitivity. We also have A determines C, and then C determines B. More? B determines A. Okay? So after applying transitivity in the Armstrong axioms, we have 3 more. So if we look at these 3 and then go back to see whether we can fill that out, would this be in any of them? No, right? Because none of them has both B and C. Okay, how about this one? It will go here. Okay. So we can write C determines B right here as well. How about this one? It goes up here. Okay. So we have okay. It's getting a bit messy, but I'll keep going. So right now, we got them all, and we can take a union of the 2 projections. Okay, so if you take a union, what do you get? You get all these 4, right? I'll just write union. Okay, all these 4. And do you get more than that? If we put 4 of them together. A determines C, which comes from A determines B and B determines C. Which else? We go this way, and we have C determines A. Okay? So in total, when we have them together, you see we have A determines B, B determines A, B determines C, C determines B, these 4, plus A determines C, C determines A. Alright? And before we take the closure, we go back there. Are they matching? This is the same as that one. So this shows you, okay, this is messy, but this is the final one. So this decomposition is dependency preserved. Okay, if you want to make it a bit more solid, you can say it's because you found AB taken in union BC the projection and take the closure. That's the same as the original closure. Okay. Is it clear or is it kind of confusing? Okay, so that's how you would check when you are given an example, how you would check whether it is dependency preserved. Okay, so until now we have learned 2 types of decomposition way of checking whether the decomposition is good. But, however, a lot of times when you are given a schema and you are the one who wants to decompose it, it might be hard to start. So there are some standard ways you can do it. We call it normalization, which I'll talk about next. So for normalization, we can use algorithms to convert relations into either Boyce-Codd normal form or Thorne normal form, which are the 2 most commonly desired. Okay. So a couple of things to note when you really try to decompose, or maybe in your project, you might be able to notice when converting a relation R into Boyce-Codd normal form, it is possible to lossless join decompose it. However, it is not guaranteed to be dependency preserving. But if we only, today, let's say we only target on third normal form, there's always a dependency preserving and lossless joint decomposition. Okay? We won't try to prove this here, it will get way too complicated, but I will show you a couple of examples when the Boyce-Codd normal form won't be able to be achieved, but we can do it third normal form. Okay. So let's discuss these two separately. Let's try to approach decomposing into Boyce-Codd normal form first, which remember is the strictest normal form, right? So this one, decomposition into Boyce-Codd normal form. We actually have an algorithm, and that's from one of our observations we have observed last time. So the algorithm only has two steps. In the first step, suppose that the relation R is not in Boyce-Codd normal form, that's why we want to normalize it, decompose it. Then let X, set of attributes, being a subset, strictly a subset of R, A be a single attribute in R. Okay, so it's not a set of attributes this time. Now A is just a single attribute. Then X determining A be a function dependency that causes the violation of Boyce-Codd normal form. Then, can you recall how we will want to decompose this? Well, the answer is actually in the same slide. How will we want to decompose them? We want to decompose them into R taking a set difference from A, with A, and then XA unique. And I'll show you how it works later. So if you notice that, then you do these steps, and if either of these is still not in Boyce-Codd normal form, all you can do is to further decompose them, repeating the same step, and keep going. Okay, until all of the decomposed relations we found are in Boyce-Codd normal form. Then we're satisfied. Okay, then the algorithm stops. But it's also possible, just keep in mind, it's also possible you will never get to a point when all of the relations are in Boyce-Codd normal form. So let's take a look at this example, which we have seen before, which is the contract schema. And today we want to decompose it into Boyce-Codd normal form. And in the past, when we used this example, we didn't have the four functional dependencies. Okay, so this one is added today. And for the second one, when we are working through here, let's just ignore the second one for now. Okay, so I grayed it out. All right. So when we talked about this example earlier, we decompose this whole R into these two sets, and before we showed that it was lossless join decomposed. Okay. And also, let's take a look. Do you think this one is in Boyce-Codd normal form if we put SD as the key for this relation? Do you think it will be Boyce-Codd normal form? It carries the function dependency of SD determining P. If you recall the rules for Boyce-Codd normal form. It is? How about this one? C is JDQV. If you take a look, it has this J determining S right here. But for this one, the key is C. Then do you think this one is in Boyce-Codd normal form? So no. Okay. So the upper one, all right, yeah, decomposed because of the SD determining P. And for the upper one, it is not in Boyce-Codd normal form. And the second one, it is in Boyce-Codd. So because we found, so here I forgot to mention, here we decompose it because of SD determining P. Okay, and if you recall the earlier algorithm, when we try to decompose it into Boyce-Codd normal form, remember we say we have the whole R decomposed into R minus A and XA. So right here the A is P. So if we have R minus A, then that's the whole thing minus P. That's why we get that. And with the second part we want to decompose is XA, so it's just basically X taking union with A. That's SDP. Okay, that's how it comes from. So now we found here it's not satisfied yet, so we want to further decompose it. Okay, so earlier we found which functional dependency is the one that violating Boyce-Codd normal form. Out of these. This one, right? J determining S. That's bothering us. It's making it not Boyce-Codd normal form. So we want to decompose it based on this fourth one. So what would you do if we repeat the same steps? Like earlier in the rule, we have X determining A, right? So here is the A, and then we want to have here, taking out the A. So the whole thing, take out S, will be the first for the decomposed relation. And because this is X, this is A, so taking the union for them, which is the XA, is the second part. So it's JS. All right. So if you take a look, if we have another further decomposition, and it is caused because of this, okay, it will become these two. Okay, as I said earlier. So if you take a look again at that point, do you think they're both in Boyce-Codd normal form now? So for here, we can say if J is the key, then this one is in Boyce-Codd normal form. How about this one? Is there any other that's bothering us now? And we say ignore this one. Then you should be fine, right? So now from here all the way to here, we decompose twice. Then all of the sub-relations now are in Boyce-Codd. Okay, so up until here, we are trying to ignore the second function dependencies. So that is actually causing us a problem if we want to talk about, we still want to check the JP determining C. So let's take a look at here. So recall last time we say if you do a lossless joint, maybe you lose the ability of checking some functional dependency, some integrity constraint. So when we want to check it, you take the decomposed relations and you join them back. And whenever you enter a new tuple, you do it that way to check whether it's still satisfied. So we say this functional dependency, JP determining C, the one we've been ignoring, actually cannot be enforced without a join, okay, of the relations we decomposed. So the solution right here, one of the solutions is actually to add a relation with the attribute of CJP. Okay, or you want to say JPC, doesn't matter. Okay. So we want to add a relation with those attributes. So that's like a new table. And you can put it maybe here. Okay. You can put it right here, so we decompose actually into these. Okay, one more right there. So that every time you're entering a new tuple and you want to check whether this functional dependency is satisfied, you just have to check that subrelation. Okay? Then you don't have to take back the join of the other relations. However, is that a redundancy over there? It actually is, because you store the repeated data, right? So here's the redundancy. And that's kind of a trade-off you have to face when you want to really go to Boyce-Codd. Okay. So right, like here, what I say, so storing redundant information, that's CJP is redundant, but it makes dependency enforcement cheaper in terms of whether you need to join. So join sometimes can get expensive, and that one makes it cheaper. So it's just kind of like looking it up like a dictionary. We have a few notes on decomposing into Boyce-Codd form. So as we saw earlier, when we were decomposing the relations, I actually just told you guys, oh, because of this functional dependency, that's why we do it this way. So if you think about it, when you start from scratch, when you're decomposing it, actually there's no right or wrong of which functional dependency to choose first. Okay, so a lot of times if you choose the function dependency in different order, that might lead you to a different result of decomposition. Okay, so there's no exact answer of how it should be. And like we saw earlier, so there might not be always a dependency decomposition into Boyce-Codd. Okay, so here I have a really quick example that we can see. We actually don't know what to do with this one. So here, say we have a schema, SBD, okay? So relation R here, and SB is our key, okay? And today you're given these two functional dependencies. The first one is SB determining D, second one is D determining B. Okay? Let's just say we saw D determining B is bothering us, and we want to use that based on that, to decompose into these two. So we decompose them into SD and DB. And this time, for this one, we have S being the key and here D being the key. However, if you go back to check, now we lost the ability of checking whether S be determining D, right? Because they're just not together anymore. Or you have to join them again. So, this here we say then we cannot preserve S be determining D. Okay, so here, if you're really pushing it, trying to decompose it into Boyce-Codd normal form, then that might not be a good idea. All right? Okay, let's see what else. Okay, so now we show you sometimes transforming or decomposing into Boyce-Codd normal is pushing it, and maybe you say, okay, then let's not have Boyce-Codd normal form, let's just have third normal form. So third normal form is also an option. Then let's talk about decomposing into third. Okay? So the decomposition into third normal form. There's also an algorithm for that. The algorithm for decomposition into Boyce-Codd normal form can be used to obtain a lossless decomposition into third normal form. But as we talked about earlier, dependency preserving might not be ensured. So let me see. Earlier we said, okay, that's what we talked about. We can add a relation of that to check the dependency. Or here we want to talk about a concept called the minimal cover. Okay? Instead of using the original F to discover what are the possible way of decomposing it, we can use a minimal cover. It will seem quite unintuitive at the beginning, but you see how it works together. So what do we mean by a minimal cover? So right here, I'll give you the definition for that. So the minimal cover for F, let's see. We normally denote minimal cover as G. Okay? So G satisfies that every dependency in G is of the form X determining A, where A, the one on the right hand side, is a single attribute. Not like what we learned before. Sometimes they can be set of attributes. Right? And the second requirement is when you take the closure of the F and its minimal cover, it should be the same. Okay? The third one is if we modify the minimal cover G by deleting a functional dependency or by deleting attributes from a functional dependency, the closure will change. Okay? So right here, you can actually understand minimal cover in another way. If you want to say, where does this minimal come from? So we say it's minimal in two aspects. The first aspect is that every functional dependency in the minimal cover is as small as possible, in the sense that each attribute on the left side is necessary. We'll talk about what necessary means later. And the right side can only be a single attribute. Okay? Then the second thing is every dependency in it is required for the closure to be equal to the closure of F. So here you might be still confused, but we can look at an example to see how it works. So here's that. I'll work on here. This one. Or, okay, I'll write at the middle. Like we saw earlier in the example, you are given with a set of functional dependencies that's in F. Okay, I'll write them down now. And your task is to find the minimal cover for F. So we have A determining B, A, B, C, D determining E, E, F determining G, E, F determining H, and A, C, D, F determining G. Correct? And our goal is to find G, okay, which is the minimal cover for F. So here, what I'll do first is actually to repeat them. Okay, I'll write down first, and then what we will do is to transform from here and also delete some of the unnecessary ones. So when I write down, let's first check. Remember, one of the requirements for function dependencies in the minimal cover is that on the right-hand side of the determining arrow, it can be an only single attribute. Okay, so let's check one by one. So A determining B, it's okay, on the right-hand side, only single attribute. A, B, C, D, determining E, it's okay, E is only single attribute. Same for EF, determining G, and EF, determining H. However, here we see A, C, D, F, determining EG. On the right-hand side, we actually have two attributes. Okay, you have any clue about what we should do to transform from here? If you recall one of the derived or additional axioms for Armstrong axiom that some of you proved.
Decomposition.
Yeah, decomposition. Okay, so what would you do? Keep the left-hand side the same, right? So you have AC, and that becomes E. Okay, and then I'll keep going, and then you have A, C, D, F becomes G. Okay, so for these two, it's because of decomposition axiom. Okay, decomposition axiom. So that's how we get from here to here. All right. So that's the first thing. And let's take a look at the second thing. We want to check whether all of the functional dependencies in here on the left-hand side, that all the attributes are necessary. And what do we mean by necessary? So you can take a look. Those with lots of attributes on the left side are the suspicious ones. So let's start from this one first, okay? So you see A, B, C, D determining E. But actually, if you look at it, we already have A determining B, right? A determining B, like so. So do you think it's necessary for us to write A, B, C, D together, determining E? So how can we transform it if we already have A determining B? How can we make it even simpler? A, C, D. We don't need the B being here. That's because of A determinant. Correct? Okay, so that's from there, we transform it into here. Okay, then let's take a look at these two. Do you think there are any problem for them? Or it should be fine? Like the left side, EF, DF. Should be all right, okay? So let's pass them first. But how about when you look at here? When you have A, C, D, F, determining Mm-hmm. So
We don't need
that one. We don't need the
F.
F.
We don't need the F, right? Or in another way, you can say, if we write, what do we put F?
We don't actually need this. I mean, when ACD is determining E.
Yeah.
So F is unnecessary. We don't even need it.
That one.
Yeah.
So this one is not necessary. Okay? Remember when we talked about the rules for finding minimal, if a function dependency is not necessary, just remove that. Right? So let's take this out, even though we decompose it. Don't need it. Okay? If you don't want to forget why you do that, that's because we already derived BCD determinant. Okay? Delete because that. this one, ACDF determining G. Do you think it's necessary? Where did you find it necessary? From here, we actually have ACD determining E. And you can actually do, if we do this, what's it called?
Augmentation.
It's the augmentation, right? If you do ACD determining E and augment both sides with F, now we have ACDF determining EF, and you find an E with F on the right, left-hand side. So you can do, we have an EF that actually already determining G. So together, through what? Transitivity, we have ACDF determining G. Okay, so this one is not necessary in a sense that it can be derived from the other ones already. Okay, cross them out as well. And the reason is because of this. Okay.
So,
Oh yeah.
for that second, the second from the bottom, how can you get rid of that when you still have that F?
Oh,
ACDF.
the reason is because when you already have A, C, D together, and then that determines E, then that's more than it. Yeah. Okay, any questions for here? So after all these steps, we found these left. A determining B, A, C, D determining E, EF determining G, and EF determining H. These left are in our minimal cover for G. Okay? Anyone need more time to write this down? Or a few more seconds, or I'll put this screen down. Okay? Okay, so here, we'll just briefly talk about actually the steps we took when we tried to find out the minimal cover. Okay, so if you recall what we did before, the first thing, we tried to put them into the standard form, in the sense that on the right-hand side, they're all single attributes. Okay, so that's the first step we took when we tried to figure out the example on the board. And the second one, we said we minimize the left side of each FD. Okay, so what we did was, I think we did, we took out some of the attributes on the left-hand side that are not necessary. Okay. And the third one, we simply delete redundant functional dependencies. So sometimes we can find some dependencies in the set that can actually already be derived from other dependencies based on Armstrong axioms. Like the earlier we first did an augmentation, and then we did a transitivity, and we found there's one that we can take out. Okay. So now we have these steps. We actually have another example we can work on, or you guys can save it up to work on it at home, or you want to work through it for this one. What do you guys think? Save it up? Okay. So you can work on it when you go back, and if you found it's rather difficult, we can go through it on Monday. Okay? So let's look at the next thing. Okay, so now we learned about minimal cover. And you might be wondering why do we even need that? And if you recall, that's because we want to decompose into third normal form. Alright? So I think we are near the end for today. So if you want to decompose into third normal form, let's take a look at here. We have a couple of assumptions that we are making right here. So your goal, you want to obtain a lossless join and dependency preserving decomposition into third normal form relations. So here we have a couple of notations. As always, R is the original relation that we want to decompose. But this time we say we decompose them into R1, R2, all the way to Rn. Okay, all these little relations, we already assume they are orthonormal form. Okay, and R is given a set of functional dependencies, and this is where the minimal cover comes in. So before you do any of this checking, you already transform the F into its minimal cover. Okay, so that's what we learned about minimal cover. And here, Fi, we mean, like we talked about earlier, the projection of F onto the attributes of Ri. Okay, so that's how we denote it. So go back, that's our goal. So we do the following. We first identify the set, which we should call it N, from the functional dependencies in F that is not preserved. Okay, so now we already decompose them into these relations. But recall, like earlier we worked on some examples, they can be lossless joined, however, some of the functional dependencies are still missing that we have to actually go back to do a join to detect those things. So you first do that, identify those missing functional dependencies and put them into R. Then, next step, for each of them, for each of the functional dependency in N, we just simply create a relation schema, XA, and add it to the decomposition of R. And that's super simple, like we did before, right? We just simply take a union of that and create a new little table for it. So that's for that. Okay. They're really easy. I forgot whether we have an example for that, but before we go in, let's just quickly take a look at here. So note that when we do all those, adding those little tables, little relations, they're already in the okay? You can think about why, but they're already in the form. And also, here we're talking about if you have lots of functional dependencies in the set N that all shares the same left side, you can actually combine them. For example, if you have X determining A, X determining B, and X determining C in your N set, okay? These that are all missing from the functional dependency in your final result of the decomposition, what you can do is actually you just combine them all together, and that's because of the union axioms we learned before. Combine them all together, and them together, they together, you create just one table for that. Okay? So you don't have to create three separate relations or three separate tables of XA, XB, and XC. Instead, you just create a whole table that's XABC. I think we have time, then we can finish an example before we go. Okay, so that's this one, which is the example we have seen so many times, and the one that we weren't able to make a dependency preserving earlier, right? We only decomposed to a point, and then we couldn't make it dependency preserving. So, what we can do, actually I'm torn to work through all of them, because we actually worked through it, but I just didn't talk about how it actually should look like. So I think I can just show you the final result, because I feel like it will be really repetitive if I work through it. So remember right here, we actually worked through it all the way. And then, back then, I just said, then just add this. But this is exactly what we talked about, right? If you have something missing, then you add a new relation for that. Okay, so that's it. That's exactly the same for the example. All right? So before we go, actually I finished early today. I have a couple of things I want to discuss with you guys. Okay, so I will post homework 3 today. But homework 3 actually includes 2 parts. So the first part is from chapter 19, which is what we have been learning, all the functional dependencies and normal forms. Okay, and it also includes chapter 5, which we will start next Monday, and that will be all the SQL programming. Okay, and for both parts, I actually think the workload is a bit high. So I've been thinking whether you guys would prefer you start working on the first part, which is chapter 19, and do in week and then the next part due in another week. But them together combine the grade for your homework 3. Or you guys want me to post it and then collect it all after 2 weeks?
All of it.
Yeah, all of us is fine.
Okay, okay, just want to help you guys out because I'm always like waiting until the last minute. Okay, you guys are cool with that, and that's all right. And bring your laptop next Monday. And if you recall, we have presentation next Thursday, right? We'll be having pizza, yeah. And we want to decide the time now, okay? So we will be needing 2 hours, I think in total for everyone to finish presenting. So that's why I'll prepare food for you because I feel bad, it's dinner time. And also, it's okay if some of the teammates really cannot come, okay? As long as there are some people that are here. But you can't just don't come, saying, there's that one, he will present it all. So you can only not be here because you have to work or because you have other classes, okay? So here you have different options. We have 5 to 7, 6 to 8, or 7 to 9. Or you guys want to do 8 to 10?
7 to 9, 8 to 10.
Okay, let's vote. Okay. 5 to 7, 6 to 8, 7 to 9, 8 to 10. Who wants it? 5 to 7. It's all right to raise your hand. Don't
We have a class at 8:30.
You're giving him look. Okay.
Oh no, sorry. He forgot.
You're putting pressure on your friend. All right. 6 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Ooh. 9, 10, 11, 12, 13, 14. All right. 7 to 9.
Which day is that?
Thursday. 7 to 9. 1, 2, 3. Who wants 8 to 10? 1, 2, 3, 4, 5, 6. Oh, okay. Then we'll just send 6 to 8. All right, and we'll decide the flavor next week. And I'll send an email again to remind you guys.